Hello, my name is Deniz and today, with my friend Umut Tosun, we will present our graduation project called Design of a Software Tool for the Simulation of Plasmonic Particles, supervised by Professor Dr. Özlem Özgün. Now, here you can see the outline. We will start with the introduction. When an incident light meets a metallic nanoparticle, in the interface metal dielectric interface, the light is confined in a region called the hotspot. And this hotspot intensity of the light is increased on the order of 30 to 300 and hence allowing us to break the diffraction limit, which will again allow us combine the integrated circuits and optical components on a single chip. And here you can see the examples of that in the plasmonic or optic circuits, in communication, or even in the spectroscopy. Now, in the problems like plasmonics, the exact analytical solution is very hard and cumbersome, and for that reason we have employed the finite difference time domain method, which is a numerical method based on discretizing the problem space and time, and also based on discretizing the defining dynamical and differential equations. Now here's what a simple point on a finite difference time domain grid looks like. If you combine all of these points, you can get a problem space where you can visualize step-by-step propagation of light. And here how it is done. First, we convert the differential equations into the difference equations. And here are the defining laws for our system. Now, as an example, you can see Ampere's law in its open form. When we apply the discretization to this formula, we can see at the bottom the main formula for electric field, and we can also write a formula for the magnetic fields. In order to simulate our problem at hand, the plasmonics, we need two things. We need definition of a source and we need definition of a problem geometry. Now, our problem requires light source, which is a laser, and it operates on the region of wavelengths of nanometers, and the gold nanoparticle, which is on the order of nanometer levels too. And here is our proposed system for the solution of that problem.
Hi, I am Umut Tosun. I am in charge of developing the GUI part. We have used MATLAB and MATLAB App Designer to implement the sources and materials. We have designed a graphical user interface where user can input the parameters of the light source and the geometry. We have implemented a user-friendly GUI where user can interact with problem and define sources, geometries easily. Let us make a final demo. When user downloads the program, there will be a file like this. By clicking the setup and simply following the instructions consist of next, program will install and the shortcut will appear in the desktop. Program runs without needing any external tools such as MATLAB. This is our GUI. In the file menu, user can open file or quit the program. User defines the geometry in the structures menu and enter the necessary input parameters. User types the inputs and clicks OK button. The critical thing is number of spheres is allowed to enter only once for the first time, as you see. Also, you can download the spheres, zoom in or zoom out and return the initial state. These entered values are returned to the main GUI. User can select the sources. Invalid user input is avoided. Let's type the inputs. As you see, plotting is updated in case of typing each parameter properly. Other sources work as well. For plane wave and the Gaussian. When pressed run button, program solves FDDT updating equations based on given parameters. As a result, program is able to introduce the required parameters for the simulation of plasmonic particles. Results are shown. A GUI was developed based on the requirements of a program that simulates plasmonic nanoparticles, and the GUI works as expected. When user hit the run button, the program needs to run the FDDT updating equations both on free space and metal dielectric interface.